All right, so I want to talk about the geostrophic balance and tell you what that is. So if I write down the momentum equations that we've seen last time, the substantial derivative, or the acceleration, dv dt, plus the Coriolis force, 2 omega cross v, where omega is the spin axis, the spin vector, is equal to minus 1 over rho gradient of pressure, the pressure force, the force due to the gravitational potential, where phi is the potential, which is the sum of this, that produces the sum of the centrifugal plus gravitational force, and finally the viscous forces, v vector. All right, so this would be the momentum equations, and what we mean by the geostrophic balance, it's a balance in the horizontal components of the momentum equations, and it's a dominant balance between the Coriolis acceleration, Coriolis, and the pressure force. In other words, if we were to take the ratio, the magnitude of the acceleration to the Coriolis force, we would find that this one is much smaller than this one in magnitude. Similarly in the horizontal, well, this one is simple. There's no gravitational force in the horizontal. It's all in the vertical, which will contribute to the hydrostatic balance. And then the viscous stresses, or the friction, is assumed small compared to the other terms. So not necessarily zero, but small compared to either one of these two. So the geostrophic balance, then, I don't need to write it again, the geostrophic balance is obtained from the horizontal components balance between these two terms. So I can write it this way. I'll write in red minus 1 over rho. And here I mean the horizontal component of the gradient of the pressure force. And on this side, we want to retain the horizontal component of the Coriolis force. So we'll write it as F z hat cross v, where z hat is the local vertical direction. So this is the Earth. Omega is the spin axis, like this. And if this is the center of the Earth, and this is the latitude phi, and then z hat is pointing outwards, normal to the surface of the Earth, or normal to a geopotential. Then we can break down omega into two parts. If this is omega, we can break it out into a component in the vertical and a component along the horizontal. And so this component in this direction is going to be omega sine phi, the vertical component, and this part will be cos phi, omega cos phi. And we call this part here F. And so, sorry, this is not F. 2 omega sine phi is what we call F, because it's twice that component. All right, so this now becomes the geostrophic balance. If I write it out in component form, it's x hat, y hat, and z hat. 0, 0, 1, that's the x hat vector. The z hat vector, sorry, is just a 1. And then I have the three components u, v, and w. And so the x component is just going to be minus v of f of z cross v. So this is going to be minus f times v. And then the y component will be minus 0 minus u. So this will be plus u, plus fu. And on this side is equal to minus 1 over rho dp dx and dp dy. All right, so this is what we call the geostrophic balance. So we can think of it this way. If we write down, rewrite it again, f z hat cross v, which is equal to minus 1 over rho grad p. So the first one is written in, oh, this is the horizontal part. So this is the geostrophic balance written in vector form, and here are the components. Somehow this marker is not working very much, like that. So if I now write down, if I look down on the Earth, so this would be, let's say, y, which is northward, and in this direction, x, which would be eastward. And then I imagine there's a current in this direction, v, right? Pointing in this case in northeastward direction. Then I can compute what, suppose we're in the northern hemisphere. So F is positive. So z hat cross v that the z hat, right, is the part which is perpendicular to y and x. So if we're looking down on the Earth, the z hat vector is pointing out of the board. Right? It's coming out at us, the z hat vector. And if I cross z into v hat, then I use the right-hand rule and sweep this into here, and my thumb, which is in this direction, is in the direction of z hat cross v. So it's going to be at 90 degrees, and it will be pointing z hat cross v to the left of v. This then is the direction of the pressure force. And remember, the pressure force points from high to low pressure. So that means we must have a high pressure on this side, high pressure, and then a low pressure on this side, low pressure. So if I was to draw lines of constant pressure, they would look something like this, and the current would be flowing along the lines of constant pressure with the high pressure to the right. So in other words, if I write all these forces on the same side, this coriolis of acceleration plus 1 over p is equal to 0. So that's the geostrophic balance. The current goes along lines of constant pressure such that the high pressure is to the right, at least in the northern hemisphere. If I go to the southern hemisphere, then F, which is 2 omega sine of the latitude, becomes negative, and then it will be the high pressure to the left of the current, the direction of the current. Okay, so that's the geostrophic balance. We'll come back to it again when we talk about the Rossby deformation radius.